1. And this time, actually, we are moving to the formal discussion of derivatives. Specifically, that is section 3.1, the definition of a derivative. And in order to give a definition for the derivative, we still need to take a quick look what we did in the beginning part of chapter 2, section 2.1. Remember, we got a little bit of discussion of tangent lines, and also we posed the question, the slope of tangent line. And the tangent line touches the curve exactly at one point. So if you think very carefully, it's very hard to answer the question directly, because to find out the slope of tangent line for any line, we always need to have 2 points. So what we discussed before is, to find out the slope of the tangent, say specifically at this point, or if you look at the lower part of the chart here, this is the situation we are studying. There is the green line, it's a tangent line, and it touches the curve exactly at one point. So to find out the slope of the tangent at this fixed point, what we did here is we choose another point which is not too far away from this given point. And indeed, that would give us a tangent line, the orange line here. And also it's worth to mention the part A and the part B, really, they are denoting the same situation, okay, really, exactly the same. Just different ways to represent the situation. A, it is a fixed point on the graph. A is a fixed point on the graph. And then we choose another point which is not too far away from this A. It is denoted by x and f of x. And then indeed, x really will have to be very close to A. And also on part B of the graph, we just want to emphasize the x cannot be going too far away from A. So we denote that x by A plus h. H is a small gap, a small change. So from point A to A plus h, they should be close, right? If we make h really close. And then indeed, when in the end, we are going to make this h approaching to 0. So at this moment, I'm saying those two graphs really are for the same situation. And also, I hope you still remember the slope of the tangent can be approximated by the slope of the secant. And indeed, the approximation could be better if we move the other point closer to that given point A. Okay, from x1 to x2, the other point is getting closer to this given point. Hopefully you see the secant line, it is getting closer to the tangent. So certainly the slope is a better approximation. The slope from the secant, it is a better approximation to the slope of the tangent. Again, part B of the chart, really it is the same situation. Just different ways to denote the situation, okay? Denote the other point. We want to emphasize the other point, it is really close to A. And indeed, I want to say somewhat you really want to give a try. Later on, indeed, I think we are going to use this second format, okay? Second way of the second representation of this same situation using A plus h, f of A plus h a little more, because in the formalized definition, this is really the better situation, better way to define the derivative, especially when we consider derivative as a function. That's the topic in section 3.2, 3.1, 3.2, really for the same topic, definition of a derivative. To this moment, I suppose we understand the slope of the tangent can be approximated by the slope of a secant. And furthermore, as x approaching to A, the secant lines are approaching to the tangent line. And accordingly, the slopes of secant lines are approaching to that of the tangent. So indeed, that is a limited process, right? Like as we discussed in chapter 2. Chapter 2 is the introduction of calculus. And most of the time of chapter 2, we consider limit. So indeed, what I stated the situation, or what I understand the situation, it is a limit process. The slope of tangent m10, this is slope of tangent, it is considered as the limit as x approaching to a of this slope, right? The slope, it is difference quotient. The derivative or slope of tangent, it is the limit of the difference quotient. And this is the situation exactly represented in part A of the graph. And also, as I'm saying later on, we are going to evolve into the representation in part B of the graph. So accordingly, if we use the representation in part B, the tangent, slope of tangent can be written into this limit. Okay. So first example related from the textbook, example 3.1. Very simple function. We are looking at the parabola, right? Squaring function. We want to find out the equation of the tangent line to the squaring function at x equals 3. First, get those simple things ready first. In general, to find out the equation of line, we use the point slope form. This is the point slope form I talked about, and x naught, y naught are the given point, given ordered pair. Okay, x coordinate and y coordinate. M is the slope. In this case, I hope it shows clearly at x equals 3. So x naught is 3. Accordingly, y naught is x squared, which is 9. So we do have this given point, x naught and y naught. And the only thing we need to find here, it is the slope. Slope of the tangent, right? Did we say the slope of the tangent, it is this limit? So I did my calculation here. Okay, I copied on the formula, copy and pasted the formula, and then plug in numbers. Clearly, a is 3, and x is approaching to 3. And then if you look closely, this is a limit, right? Remember, to find our limit, really, in the end, we always consider direct substitution, plugging value. But you see, again, in this, even though this is a very simple situation, we cannot plug in value directly because that is going to make a denominator 0. And hopefully, I suppose we do know handle this situation very well. And the numerator can be factored. And then this bad part of the denominator is cancelled, right? X minus 3 is cancelled. So the limit turns out to be the same as the limit of x plus 3. And to this moment, there's nothing wrong to consider direct substitution, right? Replace x with 3. So the limit is 6. Keep in mind, this time the limit we calculated related for the slope of the tangent. So according to the point slope form of a line, the equation of the tangent line is such. And also, if you want, we could generate this is the so-called slope-intercept form. And also, to show the situation somewhat, you may want to know the graph. It is a parabola. I mean, the graph part of the chart. It is not joined to scale. Okay, this is one along the horizontal direction. 5 actually, it is shorter. Okay, but anyway, it does show the idea. We are having a parabola open upward, and at x equals 3, there is a tangent line, the blue line here. And we do know the equation of the blue line precisely. Okay, you see the drawing looks like well, the y-intercept is 9, negative 9 here, x equals 0. The y-intercept should be negative 9, right? And the slope is positive 6. And in reality, if we make use the same scale for x-axis and the y-axis, the line goes up very fast because slope is 6. So we are considering derivatives in section 3.1. At this moment, we say, well, really, I should say, well, consider slope of tangent, and you really should consider the slope of the tangent. It is derivative. How about let's take a look at another example. I guess we should have a little more time here. Okay, this is also an example from the textbook 3.3. It's to find out the equation of the tangent line to the graph of y over x at x equals 2. So this time, what I did here is I know the slope of tangent, it is a limit. It is a limit. So I copy and paste the limit again. Okay, and then I did the actual calculation. A, it is 2. X is approaching to 2. And then the function, it is a rational function, 1 over x minus 1 over 2, right? Denominator, that's x minus 2. And again, remember to calculate a limit with factorization, with common denominator. Especially, this is the case we are having a complex fraction. So one approach to handle a complex fraction, you want to multiply numerator and denominator by the common denominator or denominator from the top and the bottom. And in this case, actually, it is just 2x. So I multiply this top by 2x, bottom by 2x. And certainly you don't want to cancel 2x for now. What I did, I multiplied this 2x, multiply this out, the numerator part out. So it just turned to be 2 minus x. And I did nothing for the denominator. Okay. After multiplying numerator out, I'm having 2 minus x on the top. And there's x minus 2. I hope you see they are close, right? And they differ by a constant -1. So 2 minus x, x minus 2 is cancelled. There's only -1 left. And that 2x in the denominator still stays. So the limit, it is really turning to be in the fashion of -1 over 2x. Remember to find our limit. We consider direct substitution. And all the work we did because we realized direct substitution cannot be done in the beginning. And now, after the manipulation, the direct substitution works perfectly fine. I simply replace x with 2, so I get a slope that's -1/4. Okay, this is example 3.3. Find out the equation of the tangent line. What I did so far, it is the slope of the tangent, which is a limit. And indeed, we figured out a limit that's -1/4. So again, using the point slope form, okay. The point, it's worth to mention, at this given point, x equals 2, because the function, it is a reciprocal function, 1 over x. Y is 1 over 2. So using the point slope form, I have the equation of the tangent line in this fashion. Y minus 1/2 equals -1/4 times x minus 2. This is the equation of the tangent line. And also, if you want to see the equation of the tangent line in the slope-intercept form, I forgot, I need to fix this here. -1/4 times x plus 1. You multiply this out, get a -1/2 to the other side. So this is the equation of the tangent line. So we are in section 3.1. And we are considering the slope of the tangent. So far at this moment, we are saying the slope of the tangent, it is a limit. And there are two formulas. I say those two formulas are equivalent. Really, they are generated according to those two graphs. These two graphs are the different representations of the way to choose the other point. But anyway, really the same idea. The other point will have to be really close to that given point. The slope of the tangent, it is the limit of the difference quotient. Okay, and indeed, in our next video, we are just going to say this kind of limit of difference quotient, simply it is the derivative. But anyway, let's take a break, and thank you for watching. See you next time.